My name is Alisher Sanetullaev. I'm a physics professor at Uzbekistan University, and today I will be talking about secret of life and nuclear physics. I will be talking about how a state in carbon affects the emergence of life. So you might be thinking how nuclear physics and life can be related. They are two different things. But in nuclear physics, we study different elements, and one of the elements is carbon. And the emergence of carbon is very interesting, and we know that life is made of carbon. We talk about organic chemistry, organic life. Organic means carbon. So how carbon emerged, how carbon came about, is a very interesting topic. And I will explain how carbon came about in stars. So origin of elements is a very interesting topic. In nuclear physics, we want to know about how different elements came to be. So in school, we learn about Mendeleev's table or chemical table of elements. In nuclear physics, we talk about nuclear chart. So in nuclear physics, we have not only the elements, but isotopes. For example, each element can have different isotopes. For example, proton or hydrogen can have different types of hydrogen, heavy hydrogen or deuterium or tritium. And different isotopes, for example, carbon has also different isotopes. For example, carbon has 6 protons and 6 neutrons. But there are also isotopes, carbon-14, for example, that have different number of neutrons and protons. And how is it related to life? The reason is we want to know how carbon originated, the origin of carbon. So scientists found out that carbon is made in stars, and then it was released into the universe, and from that carbon, life emerged. We have life. And now we want to understand how carbon came to be in stars. So we have knowledge about elements that are forming. For example, we talk about thermodynamic reactions, thermodynamic fusion. In stars, we have hydrogen. So hydrogen and hydrogen, they fuse, and several hydrogen, they come and they turn into helium. Okay, so we understand how helium is formed in stars. Actually, this is how the energy is made in stars. So our sun is shining because of this fusion reaction between protons. But now the question is, where do we get carbon? It turns out it is very difficult to get carbon because in stars we have helium. And typically, to get carbon, we would fuse 3 helium nuclei together. And to fuse 3 helium nuclei together, so first we would have to fuse 2 helium nuclei together. This would form beryllium, and beryllium 8 can be formed. And then on top of that, we can add another helium. So if we add beryllium nucleus and helium nucleus, we obtain carbon nucleus. So that would be easy, right? And then we could get life, we could get DNA, all these proteins and organic chemistry, and that's how life emerges. But there is a problem. It is very difficult to get 2 helium to fuse, and obtain beryllium. The reason is beryllium-8 doesn't exist in nature. So when you have two helium, they don't fuse together. They cannot wait for the third helium. So if they go back to being helium, how can you get the third one? So that was a mystery for a long time. People couldn't understand how can you get three helium together, because you cannot get even two together. How can you get three together and make a carbon? And if they calculate, there is a probability of getting three helium together. They have to get together at the same time. And then the probability is very low. And if you calculate the amount of carbon in the universe, we would get millions of times less carbon than it is possible now. Then life wouldn't exist. So how can you explain this abundance of carbon? Salpeter in 1950, about 70 years ago, and Hoyle, they proposed a state, so-called resonance state. Basically, they said, okay, this two helium, when you fuse them, we can form beryllium, and they can stay as a resonance, so-called resonance. There is a quantum physics as well. So in quantum physics, you can have resonance states that are short-lived, and two helium can stay for a short time, and in this time you can add the third helium, and then the problem is, even then, this carbon shouldn't exist. Why? The reason is of quantum physics. In quantum physics, we have quantum states. So when three helium get together, they have different energies. And this energy of three helium, when they get together, there is no corresponding state in the carbon quantum system. So the states are like steps. So when the three elements get together, there's nothing to step on. So they go back to three helium. So that was a big mystery. And then Hoyle suggested in 1950 that there must be a quantum state above. That's so-called resonance state. If that state exists, then carbon exists. If it doesn't exist, then carbon doesn't exist. So the hunt was on. Now they want to measure this, find this state, so-called resonance state. I mean, it must exist, because if it doesn't exist, how can you explain life? So in the 50s, they measured these quantum states of carbon. Carbon has, it's a quantum state, so quantum state means they can have quantum energies. The ground state and the higher quantum states, and these states can be measured. They have discrete states, discrete levels that are known, and you cannot change them. For example, for carbon, the zero energy is the ground state, and then you must have, for example, energy at 12 mega electron volts, and so on. So when the experimenters measured these carbon quantum states, they found the state to be exactly where Hoyle predicted. So that this state is there when three nuclei get together, and their energy will be exactly equal to the state of this resonance state. And then they can step onto it. So it's like a stepping stone. So there's a state that's like a stepping stone, and then you can step on it, and then it can go back to the ground state, it can exist. Otherwise, if the state didn't exist, then there would be no stepping stone for the three alphas to get together, and they would go back to being alphas, no carbon. So it's almost a miracle that this Hoyle resonance state exists, and it can explain the abundance of carbon in our universe, and consequently it explains the presence of life So it is amazing that we have so much carbon in our universe, in our solar system, and now we know that we are made from solar dust. So the carbon released from a star that exploded went into us, into life. Actually, this carbon was released from a star that existed before our sun. Billions of years ago, our sun is a new star. Before our sun, there was another sun that exploded and gave all these elements, and from these elements formed the solar system of planets, and with our sun. And in those planets we have carbon, and in those planets we have, because of that carbon, in Earth we have life, DNA, proteins, and so we exist. So this is a very fascinating story of life existing because of carbon, and we can explain the abundance of carbon using nuclear physics, and these studies have further effect on science. So right now there are still a lot of scientists finding similar things, similar resonances, not only in carbon but other elements such as oxygen, and this has actually sparked a lot of interest in other elements, and it will actually be very interesting topic for many years, because it has effects not only in nuclear physics but chemistry and material science. So we will be also doing some research related to this kind of resonances, and so there's a lot of experimental work to be done, and there is a lot of theoretical work to be done, and this kind of relationship between basic science and everyday life is fascinating. And now at our university, we have a master's program in modern physics, as well as PhD programs in physics and elementary particle physics, astrophysics, and some of the students will be doing research related to the topic I just talked about. So I invite future students who are interested in physics to do masters and PhD at our university. Thank you.